A while back, I made a video, I think it was called Sleeping Grad Student, where I was talking about a homework problem that I had been messing around with and trying to solve, but I was really not getting anywhere. And yesterday, our instructor, our analysis instructor, gave us the solution to the problem. He does allow us to request him to solve some of the harder, more challenging math problems if we can't get anywhere with them. So he gave us the solution to this one, and I'll show it to you here in case you don't remember it. Phi is a real valued function of a real variable. It's continuous, 2pi periodic, and we want to prove the following statement. The integral from pi to infinity of phi x over cosine x plus log x converges if and only if phi x is an odd function. Okay, so just as a few things, phi being odd means that phi of x is equal to negative phi of negative x, which means it's reflected about the origin. And this integral converges, so log x here. So log x is the natural logarithm. When you get to this level of mathematics, specifically after your second year typically in undergraduate mathematics, there's really no reason to consider different bases of logarithms. So we just kind of go back to the LOG to refer to the natural logarithm because it's the one that more often than not makes the most sense in context. It's that the derivative of the logarithm is 1 over x, which is nice and predictable. And when you use a different base, you just have to put in a correction factor, which it's like, why even bother with the correction factor at that point? Anyway, I'm rambling here. It's really nice to use the natural logarithm. That's kind of the biggest reason why we use it. And so we use this LOG instead of LN. Okay, so we want to prove this thing. This proof is very long and difficult, and there's no real way I would have been able to do it without a lot of hints. So I don't feel too bad about not working on it, but I still kind of wanted, had I solved it, I would have been really happy, but it wasn't going to happen without a lot of help. But anyway, I have the solution here. This is the solution the instructor gave us. I tried to recreate it exactly as he gave it to us, so let's stop talking and actually do it. The first thing we want to do is rewrite the integral as a sum of definite integrals. So we go from pi 2k minus 1 to pi 2k plus 1 because phi is a 2pi periodic function. And then we want to apply the intermediate value theorem, which says that the difference between log x and log of 2pi k, and the reason that we choose 2pi k is because it's the halfway point between the upper and lower limits. That difference is less than or equal to pi times the derivative of the logarithm evaluated at the lower point we can choose, which is 1 over that point. So the pi's cancel, and then we're left with 1 over 2k minus 1. And so now what we want to do is look at the difference between this function, 1 over log x plus cosine x, minus 1 over log 2pi k plus cosine x. So that's like the halfway point. And I believe the reason that we're looking at the difference here, notice that there's no phi here. I think it's because phi is a continuous 2pi periodic function, which means that it's bounded. So you can throw in that upper bound and then just pull it out of your integral, and then you're really just looking at this difference. But again, I wrote this up, so I'm kind of talking myself through it as I'm going through it here, because sometimes, that's what you got to do when you're studying these difficult problems. Anyway, so we want to look at this difference. So we establish like denominators. We find an upper bound because we make the denominator smaller by choosing the smaller point. Or excuse me, you make the denominator smaller by making the, You make the fraction smaller by making the denominator, what am I saying? You want the fraction to be bigger. It's less than equal to. So this is less than or equal to this. So to make the fraction big, you make the denominator small. Okay, now I'm following along. So the cosines cancel in the top, so we're left with the logarithms. And we just showed that this top here is bounded above by this guy. So that goes here. And then the bottom, why is it just 2k minus 1 pi? I guess we're still making it smaller, which I don't really know why we care about that too much. Hold on, maybe I made a mistake. I don't think I did. I copied it down. Oh well. I remember that this overall behaves like this, so I'll just go straight to here. I don't think there's a mistake here. It's just, I don't know why we lost the 2k minus 1 pi. I think it's because it's just a constant. You're taking the log of something that behaves like k inside up to a constant multiple. And if you subtract something from it, it doesn't feel it too much when you're at infinity. This is the part where rigor gets thrown out the window. Okay, whatever. This fraction here behaves a lot like 1 over k log squared k when k gets really large. So again, and we're looking at asymptotics here, which means that we can rewrite our summation up here like the sum of the integral from, again, the same upper and lower limits. But now we have phi x over log 2 pi k plus cosine. So we've replaced the log function with just a constant. And then we have our error term over here plus big O of this fraction, 1 over k log squared k. And this part doesn't hurt us. This is just an error part. So we really just want this to converge. If this converges, then everything's fine. So up to this point, everything has been if and only if. So we haven't really stated like, okay, assume this, then this, or assume this, then that. Everything up here is if and only if. If phi x is an odd function, so now we're starting here and going this way. This way, by the way, is the easy direction. If phi x is odd, then the integral becomes 0. Because we're over this interval here. Remember, at the center point, phi x is going to be equal to 0. And so the negative part eats up the positive part, so to speak. And so the integral becomes 0, and so we have convergence. So everything's kind of nice there. And now we want to prove the opposite direction. So the opposite direction is the most challenging bit. I mean, this bit's not really obvious to come up with on your own. You need help with it. But you haven't seen nothing yet, is what I'm trying to say. Okay, so we look at this guy, which is this stuff on the inside. We're ignoring phi x for the time being. We're going to throw phi x in there later on down the road. But we have 1 over log 2 pi k plus cosine x, and then we want to rewrite as a Taylor series expansion. So you have 1 over log 2 pi k minus cosine over the square of the denominator plus cosine squared over the cube of the denominator. And you just keep going on and on and on up until you get to this error term. So you go up to n, whatever n is. And then you have this remainder term, big O of 1 over log 2 pi k and n plus 2 power. Now, in order to make sense of this, we need the following remark. And unfortunately, I was being a big dum-dum and didn't write it down. So I was trying to recreate it here based on what I remembered him saying. The reason I didn't write it down is because I thought it was more like a side note, because there was a guy in class that asked a question about it, and then he was answering his question, and he wrote this down, and I'm like, okay, this may or may not be that critical in proving the thing, and I didn't want to waste paper, I guess, so I didn't write it down. But I should have wrote it down because we need it. And what essentially it says is that this improper integral will exist if and only if this integral will converge to L as ak tends toward infinity, where ak is a monotonic increasing sequence. And the difference between two consecutive terms in the sequence are not infinite, I think. I'm a bit skeptical here. I don't think I wrote it down correctly, unfortunately. So I'm going to put a question mark here. I'll put 3. Just to tell myself that there may be an issue there. I'll probably ask my instructor again to clarify. Or if you guys see what I'm trying to say here, maybe you can help me out. But anyway, the next part here is, still, going based on what he wrote at the board. So I know the rest here is correct. So we're letting AK be equal to 1 over log 2 pi k. So these are the terms of my sequence, except now I'm throwing in the phi, and I'm taking the integral of it. So I have the integral from negative pi to pi of phi. Same thing here for phi times cosine. Here, phi times cosine squared. And then you just keep going on and on up to n. And then you have this remainder term at the very end, which we don't care too much about. And so we want these AKs to converge. Otherwise, we're in deep trouble, right? But the only way for them to converge is every integral here is equal to 0. If an integral is not equal to 0, then what happens? I think because these terms out in front, when k gets really large, this 1 over log k, they diverge. Okay, I forgot for a second why we wanted the integrals to be 0. And the reason we want them to be 0 is because when k gets really large, these fractions explode and they diverge. So in order for, no matter what power you put on them, so in order for my sequence to make sense up here, I need each of these integrals to be 0. Okay, so this means that this integral is equal to 0 for all integers, all positive integers. Okay, and so now the next step is we want to replace cosine n with cosine nx, where this power goes inside here. And that can be done using trig identities. Again, there's a little bit of hand waving going on here, but he's okay with it. I think he's okay with it as long as you explain. You don't actually have to show it as long as you can explain why it works, which is what I've written in parentheses over here, using trig identities, specifically cosine 2x equals 2 cosine squared x minus 1. And you can repeat this over and over again as many times as you need to in order to get this n fully inside the cosine. Okay, so we're almost done. So now we're going to define an even function, fx equals phi x plus phi negative x. So it's not too hard to show that this function is even. Actually, it's pretty easy, because if you just plug in negative x here, you'll get phi of negative x and then phi of positive x here. So yeah, it's definitely even. Phi doesn't even have to be odd in this case, but whatever. I don't want to say anything that's not pertinent to solving this problem. So f is an even function, and so what we can see is that if we take the integral of fx times cosine nx, this is going to be equal to 0. Why is this equal to 0? It's even, 2 pi periodic. Well, cosine's 2 pi periodic, because again, we're still on the interval from negative pi to pi. I don't think it's too hard to show that it's equal to 0. This one definitely makes sense, because sine is an odd function. So that part's going to be equal to 0. I'm not seeing immediately why this is 0, but I know it's obvious because he said it was obvious, but, you know, it's dangerous to say the word obvious in mathematics, because then you forget stuff like I'm doing. But it's equal to 0. I don't think it's that hard. Oh, wait, I know why now. It's because you can split it up into these two, right? And then split the integral up and show them both equal to 0. Okay, I think I'm understanding myself now. Yeah, okay, I talked myself through it. I see it. I see now. Okay, so this is equal to 0. So since both the cosine and sine are equal to 0, or these two integrals are equal to 0, we can rewrite this as integral fx of e to the negative I n x dx is equal to 0 for any integer, positive integer n, by just combining the integrals. But these give us the Fourier coefficients. So the Fourier coefficients, whatever you call this, hat, I don't know if you call it hat or not, f hat of n is equal to 0. And then by the uniqueness theorem in Fourier analysis, we know that if this is equal to 0 for all n, then f has to be identically equal to 0. And if f is identically equal to 0, then you can just move this guy over to the other side, and you've shown that phi is an odd function. And that completes the proof. Overall, it was a bear cat of a problem. I would not wish this on my worst enemy, but at least we got the answer and we can go back over it and tear it to shreds if there's anything here that doesn't have any rigor to it. But anyway, that's the problem. By the way, we recently hit 20,000 subscribers. That is an insane amount for me. I cannot believe enough people are interested in these videos to where 20,000 people want to see what I'm doing. But I did create this channel to kind of show like a little window into what it's like getting a PhD, because it's not everyone gets one. It's a very difficult thing to do. It takes a lot of sacrifice and effort, and I don't know. If you're thinking about getting a PhD, this kind of gives a window into what it's like, more or less. I mean, you only get to see 20 minutes at a time, but I'm glad that you're getting something out of it, because that's really all I wanted to do. Anyway, thank you very much for all the kind words, and I got to prepare for my class today. Thanks.